I will first give my my plan. So what I want to do is to describe the theory, the basic things in the theory. I won't be able to do a lot of proofs because it takes time. So I will first speak of affinoid algebras and affinoid spaces, which are the building blocks of the theory. Much like affine schemes are the building blocks of scheme theory. Then I will describe the structure sheaf on affinoid spaces, which will be the main tool to glue the building blocks and to define a general analytic spaces. And the last part will be about curves. And what I want to do, I hope I will be able to do that, is to start first with the semi-stable reduction theorem for curves. And described quite accurately the local picture of a curve in analytic geometry. And then to reverse the process, first give an a priori description of the curve and deduce a new proof, kind of original proof, of the semi-stable reduction theorem. All right, so this is about non-Archimedean analysis. So just let me make a brief introduction before beginning. So what are the main features of non-Archimedean fields? So if K is a non-Archimedean field, which means complete with respect to non-Archimedean absolute value. Then we have nice properties. First, the field has topology, a metric. And we can look at power series, and it's very easy to see if a power series converge or not. In fact, if you take a series, so A, N, R in K, this converges in K if and only if the general term converges to 0. So it's very convenient. And we have some back properties. So first one is the fact that closed disks of positive radius are open. Indeed, if you look at, say, the disk centered at 0 with radius R, which is a positive real number. And if you take some point inside, well, you have a whole neighborhood of this point which is contained in the disk. Indeed, if you look at all point x in K, whose distance to x naught is strictly less than R, then this is contained in the closed disk, simply because so x is less than the maximum, less or equal than the maximum of x naught, x minus x naught. So this is less than R if x is in this subset. Okay, so a consequence, since closed disks are of positive radius are a basis of the topology, it says that the space is totally disconnected. So topology is totally disconnected. And if you have a nice notion of power series, then you cannot have a nice naive notion of analytic continuation. Another bad property is the fact that it seems quite reasonable to think that we will have to go to an algebraic closure of the field to have enough points. So one should go to an algebraic closure of the field, which will be complete. So this is completion. There is a unique way to extend the absolute value to this field. But if we do that, even if we start with a field which is locally compact, then we lose local compacity. So local compacity is lost if K is locally compact, because in fact, if you have K, or big K, say, non-Archimedean, has infinite residue field, then the field is not locally compact. And it is easy to see why it fails. You can look at all elements with absolute value at most 1. This is a ring inside K. And you can reduce, so this is, say, R. This is a ring, local ring. And you can reduce modulo the maximal ideal, which is the set of all x with a value strictly less than 1. Which is the residue field. So this is surjective. And if you take any set theoretical section, then you can write R as the disjoint union of open disks with center at the points given by the section, and radius 1. And now if you look at a sequence, in R, such that when you reduce and go to the residue field, the sequence is injective. Then what the points will do, they will change at each step, they will change from one disk to another. So there will be no point and in R and no open neighborhood which could contain the limit. And neither any subsequence, so it doesn't have any convergent subsequence. So this is a problem if you want to do some kind of measure theory, for example, on your space. You don't have the usual tools available. And so Berkovich theory, in fact, is a way to solve both problems. The first one was solved before by so-called rigid geometry, introduced by Tate and developed by many others since 1960. And in fact, Berkovich geometry is a kind of complement of rigid geometry. It's not completely disconnected. And you will see that it gives a nice way to get rid of those two pathologies. Okay, so this was the introduction. I will start the first part. All right, so like in algebraic geometry, you have to do quite a big amount of commutative algebra before being able to really develop the geometric picture. And here, the algebra deals with Barnard algebras. So this is topological commutative algebra. So what I will do is I will try to give you the main definitions and main properties on this algebraic side, and then I will state the geometric consequence. So the first part is a kind of list of what we need from the algebraic side. Okay, so one. So maybe I will stop here. First subnotation which will be used in the following. So say one notation. So we will work with a field K, which is non-Archimedean field. I gave the definition. so which implies complete. And we will denote by K0 the ring of all elements which have an absolute value at most 1. So this is a ring, local ring. K00 is the maximal ideal, which is the set of all elements with absolute value strictly less than 1. And the residue field, K tilde, so this is from the one part of the notation. Another part of the notation deals with the value group. So this is the value group, which is a subgroup of R positive. And we will have to look at this bigger subgroup, which by definition is the set of all real numbers lambda, a positive power of which belongs to the value group. And in fact, this is the same thing as the value group of an algebraic closure of K. So the main examples of non-Archimedean fields are the fields of p-adic numbers, the field of Lorentz series of a base field with the usual absolute value, and also any field with the trivial absolute value, which consists in 1 for any element which is non-zero, and of course 0 as absolute value 0. Okay, so let me just say that we will work with Banach K algebras. So just to be precise, say that A, when I say a Banach K algebra, I mean that the norm on the algebra is submultiplicative. And there is a well-known notion of spectral radius. So if A is a Banach K algebra, F is any element of A, the spectral radius of F is the infimum of norms of F to the n at the power 1 over n, and it can be shown that this is also the limit of the sequence. All right, and a last notion, we will have to take tensor products, of course, and if you want to, if we have two Banach models and we want that the tensor product has a Banach module structure, we have to force it. So we will work with complete completed tensor product. So if A is a Banach K algebra, and Mn are two Banach A module. Then we define the completed tensor product by putting a hat on the usual symbol as the completion of the standard tensor product with respect to a semi-norm, and this semi-norm is given by norm of an element x. The semi-norm of an element x is the infimum. You take all representations of x as a sum of elementary tensors, and for such a representation you take the maximum of the products of the norms. So there might be a kernel, so this is only a semi-norm, not a norm in general. You complete and you have the completed tensor product. And let me just state a fundamental fact, which in fact is a deep explanation of many phenomena which occur in non-Archimedean analytic geometry. The fact is that any non-Archimedean field has a non-trivial non-Archimedean extension. So what it means? It means that K is non-Archimedean, and the map is isometric. And this is the extremely different from what happens in the Archimedean world, because for Archimedean fields this does not occur because of the Gelfand-Mazur theorem, which says that in characteristic 0, which is automatic if you have an Archimedean norm, then there is no non-trivial extension of C. So this is failure of Gelfand-Mazur theorem. All right. So let me define the starting block. So when we want to do algebraic geometry, we start with polynomials of a field. Here we will replace polynomials by convergent power series. So this is the two so-called Tate algebras. And affinoid algebras. So they play the role of polynomial rings and their quotient. So definition. Let n be a positive natural number, and R1, Rn be positive reals. So we denote by k bracket r minus 1 t. So I use multi indexes. So this is in fact r1 minus 1 t1 rn minus 1 tn. So what does it mean? This is a notation. The set, the K algebra, I will, yeah. The K-algebra of formal power series in T1 to Tn. So which have a prescribed radius of convergence, and so, such that would satisfy the condition. So the max, sorry, condition that the absolute value of a nu times r to the nu goes to 0 when the length of the multi-index goes to infinity, where, as usual, r up to the nu is r1 to the nu 1 times rn to the nu 1. And we put a norm on this algebra. Endowed with the so-called Gauss norm. So the norm of such a power series is the maximum of those quantities Okay, so this norm gives this algebra the structure of a Banach algebra. So we get Banach algebras, Banach K algebras, called Tate algebras. And they replace polynomials in the theory. So there is a couple of fundamental facts for those algebras, which are not that easy to prove, in fact. So a Tate algebra is Noetherian, and all its ideals are closed. This is the first point. And a second point, which concerns only algebras which we get when we pick R1 equals R2 equals Rn equals 1. So if R1 is R2 Rn equals 1, so we say then that we are in the strict case. Then the residue field of any maximal ideal is a finite extension of K. So this is the notion that's in this setting. Okay, so those are the algebras which will play the role of polynomial algebras. Now, if you want to have algebras which will play the role of any K algebra of finite type, we just take quotients by ideals, and we get what is called affinoid algebra. So definition. K affinoid algebra is a Banach algebra isomorphic. So as Banach algebra, it means that you want the isomorphism and its inverse to be both bounded. To a quotient of a Tate algebra, which you endow with the residue norm. And if you can pick the real numbers are to be all equal to 1, so if we may assume, if we may get R1 equals R2 equals R1 equals 1, then we say that the algebra is strict or strictly affinoid. Then the algebra is said to be strictly affinoid. And let me just remark that in the classical theory developed by Tate and many other mathematicians after him, so-called rigid geometry, the only algebras which occur are strict. Okay, and we just say that the morphism between two K affinoid algebras is morphism between Banach algebras. It means K morphism which is bounded. So morphisms of K affinoid algebras are just the morphisms of K Banach algebras. So bounded K homomorphism. And we get, in this way, a category a full subcategory of the category of all Banach K algebras, which is denoted by K affinoid Kf. So again, there are a few facts which are crucial for the theory about such algebras. So the first I will just state it again. Of course, as quotient of Tate algebras, they are Noetherian and all ideals are closed. And now we have Banach algebras, which have some nice properties among Banach algebras. One nice property is the behavior of the spectral radius. So this seems a bit technical, but it will be useful later. So for any f in A, we can control the norm of f and its powers in terms of the spectral radius, which is wrong in general if you work with an arbitrary Banach algebra. So it says that there exists a positive constant c and some integers such that the norm of any power of f larger than n is less or equal to c times the spectral radius of f to the n. So you will see later that this is a nice property. And in particular, one can deduce from this, even if it's not completely obvious, that if A is reduced, in fact, the spectral radius gives a norm on the algebra, which is equivalent to any Banach norm for which we have this definition. So if A is reduced, then there is a constant such that for any f, the norm of f is less or equal to c times the spectral radius. And we have always have the converse inequality, of course, by the definition of the spectral radius, which is always less than c times the norm of f. So it means that we get a canonical Banach norm on A once A is reduced. And we will see how to interpret this norm very soon. And so a last property, which is in fact a fundamental fact, theorem, which is Neuter normalization in this context. So let A be a strictly k-affinoid algebra and assume A is integral. A is a domain. Then there exists a finite injective morphism from a Tate algebra, which is strict, into A, and this allows to study the geometry of Banach algebra, of affine algebras by reducing to Tate algebras. This is a fundamental fact. All right. So maybe I will stop here the preliminaries in commutative algebra. I will recall some other things later, and I will start the geometric picture. So 3. We'll attach to any affine algebra some space, which will be its spectrum in this theory. So spectrum. And in fact, it works more generally for any Banach algebra. So here is the definition of the points of the spectrum. So definition: let A be a Banach K algebra, and what I call a bounded multiplicative semi-norm on A is a function from A to the set of non-negative real numbers, so let's call it X, which satisfy some properties, satisfying. So first you want to map 0 to 0, 1 to 1. Then you want to map the sum of two elements on something which is less or equal to the maximum of the two elements. Third, you want it to be multiplicative, so the product goes to the product. And you want it to be bounded, so there exists C positive, such that for any f, x of f is less or equal to C times the norm of f. So just a few remarks. In 4 here, you can take C to be 1. Why? Because you can use multiplicativity to replace C by C to 1 over n for any n. So for any n natural number, you have that x of f is x of f to the n to the 1 over n. And so this is less or equal to C to the 1 over n times the norm of f. And so you can assume C to be 1 by taking the limit. And second condition, in fact, for any lambda in the base field K, x of lambda is the absolute value of lambda, simply because, of course, it is clear if lambda is 0, and if lambda is non-zero, you just have two inequalities. The first one says that x of lambda is less or equal to the norm of lambda, which is the absolute value of lambda. This is a constant. And the same thing for the inverse. So you get equality. Okay, so it means that any such semi-norm induces on the base field the absolute value we started with. And now the definition of the spectrum. So the spectrum M of A of a Banach K algebra A is the set of all bounded multiplicative semi-norms on A. So this is a set, and we put a topology on this set, endowed with the weakest topology So the weakest topology with respect to which any evaluation map is continuous. So with respect to which any evaluation, so what is an evaluation? You take f in A and you just look at the function of on M of A, which maps x to x of f. So you want those functions to be continuous. So now it's time to change a bit the notation, and we consider semi-norms as points in the space and elements of the ring as functions on the space of semi-norms. So we will adopt another notation. But before this, let me remark something. So remark, if you take a point in the spectrum, so you have a semi-norm on A. So this is basically an absolute value with eventually some kernel. So you can round out by the kernel. So the kernel is a prime ideal in A. And if you mod out by the kernel, you get an integral ring with an absolute value on it. You can extend the absolute value to the fraction field. You get a field with an absolute value, which extends the one on the base field. You can complete, and what you get is a non-Archimedean field, which extends the base field. So A, we take the quotient field of A by this kernel, and you put on it the induced absolute value. You complete, and you get a field which is denoted h of x. So this is a non-Archimedean extension of K, which is called the completed residue field. And what is the value of x at some element f. In fact, x of f is nothing but the absolute value of the image of f in h of x by the value construction. So, notation. When we have x in the spectrum and f in the algebra, we denote by f of x the image of f in the completed residual field, and we write absolute value of f of x, which is the same thing as x of f, and this is the notation we will use up to now. And sometimes we also write, instead of f of x absolute value, we also write absolute value of f computed at x. So this is a new notation. Okay, so we have a space of points, and elements of the algebra are functions on this space, continuous functions. And now the basic result on this spectrum is the following theorem. Or maybe first some examples, perhaps. Okay, so examples. So, how can you construct points in the spectrum of A? So, I will look at A equals the Tate algebra of in one variable, so power series in T whose coefficients goes to 0 when the index goes to infinity. And here are two ways to have points in this in the spectrum of A. The first one, if you start with some element of the field with absolute value less or equal to 1, then you can look at the canonical evaluation. So this gives you, if you compose with the absolute value, composed with the absolute value, gives a point in M of A. So this point I will denote by PA. And so this is a semi-norm with kernel, the maximal ideal generated by T minus A. So two distinct points gives two distinct semi-norms. So we get an injection of this ring inside the spectrum. So any point, bounded point in the naive sense, gives a point in the spectrum, but there are far more than only those ones. Now pick any real number between 0 and 1 and consider the following function. Which maps a power series to the maximum of the absolute value of the coefficient times r to the n. So you can check that this is a multiplicative semi-norm bounded, and what is the kernel? Well, if R is 0, you recover the point 0 in K0, but if R is positive, then the kernel is the prime ideal 0, so this is in fact already an absolute value. And you have, in this way, defined new points which are not given by elements of the field inside the spectrum. So I will give a name, say eta 0R. The kernel of eta 0R is the prime ideal T if R is 0 and 0 if R is positive. So in this case we get an absolute value on the fraction field of this ring. Okay. So maybe one more remark to make the connection with algebraic geometry even closer. So a remark, and I will then state the main theorem about the spectrum. In fact, you can, if you look at the definition, you can see that M of A as a set can be identified with the set of all bounded K morphisms from A into big K, where big K, capital K, is an arbitrary non-Archimedean extension of small k. And this is not this set, but a quotient by some equivalence relation. So modulo the following equivalence relation. You say that two morphisms are equivalent. Prime if and only if there exists a commutative diagram which means that, in fact, if you enlarge the field and contain both fields, then you define, in fact, the same map. And this is very similar to the to a way to define one way to define the prime spectrum of an ideal of a ring as a set of equivalence classes of maps between the ring and the field. All right, so here is the main theorem on the first theorem on the spectrum. Yes, maybe before. Just to, of course, we want to have a functionality, so it is easy to see that if you have a bounded morphism of Banach algebra, so say U of phi is a bounded K morphism, well, it induces a continuous map between the spectra. So we have, in fact, defined a functor from the category of Banach K algebra to the category of topological spaces. And here is the theorem, the first one, about the spectrum. So I will state it only for affine algebras. Let A be a K-affinoid algebra. Then first, the map which takes a point in the spectrum and maps it to its kernel. This map is surjective. So in particular, if the ISP spectrum is non-empty, then this spectrum is non-empty. So in particular, M of A is empty if and only if A is the zero ring. And second, the topological space M of A is Hausdorff and compact and Hausdorff. And in fact, we can remark, so I won't give the proof of this theorem, but I will just remark that the second point is the beginning of an answer to the second problem I mentioned, which is that if we extend a local field, we lose local compactness. In fact, if we take this space and not only the points in the field, we get a space which is compact without any hypothesis on the field. So 2 solves the loss of local compacity, which I mentioned at the beginning. Okay. So now let me have a look at classical points and connectedness. So I will now address the first objection I mentioned in the introduction. So what is so here we assume K to be algebraically closed for simplicity. So what we do usually in Tate's theory is the following. So let A be a strictly K-affinoid algebra. In Tate's theory, so just to say rigid geometry, which point do we take as the for the spectrum? It's only the set of maximal ideals. So we only consider maximal ideals of A. So since I assume K algebraically closed, and thanks to the Newtonian Zats for strictly Kerr-Finnoid algebras, this is nothing but the kernel of a morphism from A into K. Here, which is to say, okay, sorry. So another sentence. So, what is the maximal spectrum of A? Well, it is canonically in bijection with the set of K homomorphism from A into K. This is a Newtonian Zats. And so we get a well-defined map from this set into the M of A. And we have a well-defined map, say A, from the maximal spectrum into M of A. We pick a maximal ideal, and you look at the semi-norm which you get by mapping A to the residue field, which is K, and then you compose with the absolute value. So you get a semi-norm with kernel exactly M, so this is injective. And here what one can say so here is in fact this is a comparison between the classical setting of Tate's theory and the setting in Berkovich geometry. So proposition. So the map I is injective. This is obvious. Induces the metric topology on the maximal spectrum. I will explain what it means. And third, if the evaluation is non-trivial, which is to say that we have at least one element of absolute value distinct from 0 or 1, non-trivial, then has I as dense image. So maybe I can sketch a proof of this proposition to see how it works. So proof. So one is obvious. Since you recover the maximal ideal as the kernel of the semi-norm. So what is the metric topology? Well, if you say that A is a quotient of some Tate algebra, which is strict, then you have, so this is probably U. You have a map from the set of K morphism from A to K to the same set for the Tate algebra. Yes? No? Good. And to give a K, so they are supposed to be bounded because I work with K algebras, with non-algebras, sorry. So a bounded morphism is defined by just prescribing the images of the indeterminates, and they have to be of absolute value less or equal to 1 if you want that the power series converges. So this is, in fact, canonically in relation with the set of all elements in K with K to the n with absolute value less or equal to 1. Just map a morphism onto the collection of the image of the indeterminates. So this is a bounded subset into K to the n. Here you have the topology given by the absolute value, and you just look at the induced topology. Here you have an injection, and so you take the induced, the topology induced by this injection. This embedding. This is the metric topology on the maximal spectrum. And in fact, it's not difficult to see that the basis of this topology is given by some explicit subsets. So a basis topology is given by subsets of the form so all say U in the set of homomorphism such that while you have some functions in A, F1, and you want to be it to be in absolute value less or equal to some positive real number, with F1, Fn into A and R1, Rn positive real numbers. So in fact, you intersect the image with some polydiscs. This is the basis of the topology. Now, a basis of the topology on M of A. So I define the topology as the weakest topology which makes all evaluations continuous, but here is an explicit basis of the topology. Or more exactly, a basis of neighborhoods, because we will have a closed subset on M of A, or in M of A, is given by the subsets of the form. So this is only the pointwise topology with respect to evaluation. So you just look at those subsets, in fact. So absolute value of f1 of x less or equal to r1, fn of x less or equal to rn, and you also want inequalities in the other direction. So gen1 of x, gm of x with the fi's and j's in A. The ri's are positive, and the sj's are non-negative. So this is, by definition, of the topology on M of A. So let's call it V. And it is clear that among those you have a subset which will define exactly the basis you have on this space just by restriction. So it is clear that point 2 is true. So point 2 follows. And now I want to sketch the proof of point 3. So I assume that the absolute value is non-trivial, and I want to see that any such subset contains a point which comes from a maximal ideal. So have to see that V contains a point which is the image of some maximal ideal. And so because I assume that the absolute value is so I assume that the field is algebraically closed. So since I assume the field is algebraically closed, and since the absolute value is non-trivial, in fact this group is dense in the set of positive reals. So by shrinking a little bit V, I can assume that all radii which appear here are in this value group. So can assume belong to K. And the point now is that the set V is itself the spectrum of an affine algebra. So set B equals to okay, so I didn't define the notation, so I will just define the notation after I've written it. So S1, Sn, sorry, T1, R1, Rn, S1, Sm, modulo the ideal generated by so fi minus lambda I ri and j sj minus nu j. So where A of R1, Rn, S1, Sm is a set of power series with coefficients in A, defined exactly by the same formula as the Tate algebras in the beginning, as a similar definition to the Tate algebra in 2. So the fact is that if A itself is a k-affine algebra, which is the case, then B is also as A, B is a k-affinoid algebra, and the canonical map from A to B induces a map between the spectra which you can check. It is in fact an homomorphism onto V. So this is easy to check. And so now you just have to explain that this is has a point which comes from maximal ideal of B. And the point is, by assumption, V is non-empty, hence B is non-zero, and we can apply the Neuter Normalization because B is a strict affinoid algebra to B to get a maximal ideal M contained such that its image by the canonical map is inside M of B, and you conclude by the commutativity of the diagram so this gives you a point in the set you have picked. Okay, so I will just finish by stating another theorem, and which will be the starting point of the lecture tomorrow. So this is about connectedness. And the theorem says that let A be a k-affinoid algebra the spectrum M of A is locally arcwise connected, and it is connected if and only if spec of A is connected. So if you start with an affine algebra which has no non-trivial idempotent, the topological space you get as the spectrum is a space which is arcwise connected and locally arcwise connected. So tomorrow I won't prove the theorem, but I will give you an example with Tate algebras to see that their spectrum is connected, and I will describe more precisely the spectrum of the Tate algebra in one variable of any field.